Okay, let's consider an example. Say lithium bromide. We know it is a salt, an ionic compound. When it dissolves in water, delta H solution is equal to negative 49 kilojoules per mole. So that means that if we take a mole of lithium bromide, dissolve it in solution, then 49 kilojoules of heat will be released into the solution. So that means the solution will heat up when we dissolve lithium bromide because heat is released when it's dissolved. So if we took the steps, the first step is breaking apart lithium bromide in its respective ions. That takes energy. The second step is breaking apart water. And it's just a number, stoichiometric coefficient. So we break apart water so that it can surround the lithium and bromide ions, and then we form the solution. So this would be lithium bromide aqueous, which equals lithiums and bromines surrounded by water in their hydration shells. So these first two steps require energy to break apart the ion-ion or dipole-dipole interactions. And then this third step releases energy when the water interacts through dipole ion interactions with the lithium plus and bromide minus. So if we add up all these steps, the enthalpy, total enthalpy for these three steps added together is equal to negative 49 kilojoules per mole. So let's find the final temperature of a solution after we dissolve lithium bromide in it. So say we take 0.1 moles of lithium bromide in 1 liter of water at 25 degrees centigrade. We want to know what the final temperature of the solution will be. Well, we have heat being transferred from the solution forming to the solution itself, to the water. So we're going to approximate this as the heat for solution forming for lithium bromide dissolving, and that will be transferred to the water. And we'll heat up the water. So we have Q for solution is equal to Q water. Now water is going to gain the heat because Q solution, delta H solution, is equal to negative 44 kilojoules per mole. 49 kilojoules per mole. So this is negative exothermic. So when we form the solution, it releases heat and the water will gain the heat. So I use a plus sign for water gaining heat and a negative sign for the solution losing heat. So the sign tells me which direction energy is flowing. It's flowing out of the dissolution process and into the water. Okay, so now I just put expressions in for the heat. So Q solution is equal to delta H solution. So remember, Q at constant pressure is equal to delta H. So I have negative delta H solution, that's Q solution, is equal to positive Q water, and that's going to be MC delta T for water. So now I can solve for delta T. So delta T is equal to negative delta H solution over mass of water and the specific heat of water. So I'm ready to plug numbers in. Okay, delta T is equal to negative delta H solution. So I have a negative of a negative 49 kilojoules. That's a positive 49,000 kilojoules per mole. Okay, so that's released per mole of lithium bromide dissolved, but I need to know exactly how much I dissolve so I know exactly how much heat is released. So I dissolve 0.1 moles. So this product will be 4,900 kilojoules of heat released. And then divide by the mass of water. Well, I have 1 liter of water, that's 1,000 milliliters, so that's 1,000 grams of water. Then I have the specific heat of water, 4.2 joules per grams degrees centigrade. If this wasn't given to me, I'd look it up in a table. Okay, so this is delta T. Okay, this is 1.2 degrees centigrade. So my final temperature would be 25 plus 1.2, or 26.2 degrees centigrade. So